Hi, this is Javier Encinas, and today we're going to design completely from scratch a combined footing in a real-life example. This pipe rack, a typical structure in industrial facilities, is composed of a series of bends, like the one shown here. Each bend is composed of two columns and beams at the different levels of the rack to support the pipes. This structure can be subjected to wind or seismic if it's in a seismic zone, and of course dead loads and live loads. In this particular example, we have a pipe rack with this typical bend shown here. The distance between columns is 10 feet, and since the distance between them is so short, it's better to share the same footing rather than independent spread footings. So a combined footing is typical solution for this kind of structures. So we're going to design a combined footing for this bend in the pipe rack. The loads are dead load 20 kips, axial load in each column, live 40 kips, and the wind is 18 kips plus or minus, plus in one, minus in the other one, in uplift. The shear due to wind is 8 kips, horizontal reaction, and the columns are supported on pedestals, also a typical solution in industrial construction to protect the columns against corrosion. The allowable soil bearing pressure is 3000 psf. We're going to use ASDIP Foundation for this design. So let's get started. When you open ASDIP Foundation, the first you see is the project manager, which is this form where you can see the modules included in the package. In this case, we're going to design a combined footing. So let's create a calculation. Let's call it pipe rack. The calculation now will be created and it's added to the tree. Let's double click on the tree, and this is the calculation that we just created. Okay, let's start with the input information that we have in the example. The loads is very important information that we enter first. Dead 20, live 40, and wind 18. Let's go to loads. Let's specify a nominal set of load cases. If we select pre-formatted loads, we need to enter service and factory loads. In this case, we're going to enter a set of load cases: dead, live, roof, live, snow, wind, and seismic. In this case, is given the information as dead 20 in both columns, we said that live is 40, both columns as well. Now in wind is plus or minus 18. Let's enter that information. Wind plus in one and minus in the other one. In addition, in wind, we have a shear, so a horizontal reaction of 8 kips. Let's enter that as well. 8 kips in both columns, horizontal reaction. So basically, we have already entered the loads. Graphically, we can follow what we do here. Let's move to the geometry tab where we can enter the dimensions of the footing. We know that the distance between columns is 10 feet. It's also an information given in the example. In this case, since the footing is going to be subject to wind, the wind is reversible, can be in either side. It's convenient to design a rectangular footing rather than a trapeze. So let's input, let's say 5 feet wide footing would look like that, rectangular. We can see that the maximum bearing pressure here is 2.5 and the allowable is 3,000. So we can reduce a little bit more the dimensions. Instead of edge distance 2, let's say edge distance 1.5 and 1.5 in the other side. And the bearing pressure is 2.7 versus 3, which is okay. We can leave it the way it is. 2.7 is okay. The footing thickness, 24 looks like too much. Let's shorten it to say 18. And the water table is not a factor here, so let's put it at 4 feet deep. So it's not a factor, it's down there. Okay, so we have entered the information of the footing already. Let's move to the columns dimensions. Typically, the columns will be probably W10 or W12. So the footing or the pedestal need to be at least 18 by 18. Let's input that, 18 by 18. In both directions, both columns. You can see that graphically is changing as you enter the information. And say that the column height, the pedestal height is 2 feet. This is important because the loads are applied to the top of the pedestal. When you select that the columns are short pedestal, the loads are applied to the top of the pedestal, which is the case like this. When you have a steel column bearing on top of a pedestal, the loads are applied at the top of the pedestal, versus when you have a concrete column or a steel column but going down to the top of the footing, the loads are applied to the top of the footing. But in this case, we have a pedestal, the loads are applied to the top of the pedestal. So this is an important issue, an important information that we need to enter correctly. So the maximum bearing is 2.7, which is okay. Note that we are using the service loads to calculate the bearing pressures, and this is the controlling combination, which is a service load combination. The loads are already entered. Move to the materials. The footing, concrete is 3,000, which is okay. Soil density 120, perfect. Concrete density 150, normal weight, and the allowable soil pressure is 3,000. Okay. The columns 4,000 psi, and the concrete density is okay. We can see here in a glance view that the ratios are low. The shear ratio is 0.40, so meaning that probably we could reduce a little bit the thickness. The shear is comfortable. So let's move, instead of 18, try 16 inches. Okay, 0.50, 0.72. Okay, 16 is probably more optimized. Let's move to the graph diagrams. The program shows here the shear diagram and the moment diagram for the footing. As usual, a combined footing has a negative moment in the center between the columns and a little bit of positive moments at the ends. But this is a controlling moment. In this case is 154 cubic feet, and this is the controlling load combination. Based on this moment, the program calculates the bending ratio that is shown in the different tabs In the longitudinal reinforcement, we can see that the ratio is 0.51. Let's see what kind of reinforcement we have there. We have 12 number 6s. We can see that graphically in the construction tab. 12 number 6s top and bottom. And the ratio that produces is 0.51. So we can reduce a little bit the rebars. Instead of 12, probably one half of that, probably 6. Oh, we are very close, so we need more. Maybe 7 number 6s. Yeah, that's perfect. It's 0.85%. 85% of the capacity is used. The same thing for the bottom. So let's use a top and bottom rebars. This is typical for combined footing. For the transverse reinforcement, we can see here that also the ratio is very low. It's 0.11 in both cases. So we can reduce substantially the rebars here. Instead of number 6s, we can use number 5s. Number 5s for the interior, number 5s for the exterior. This is the top. For the bottom, we can use number 5s as well, number 5s and number 5s, top and bottom. So this is not controlling at all. This is a very low moment in this example. So graphically we can see how this looks. 7 number 6 top and bottom longitudinal, and transverse 6 number 5s top and bottom at each pedestal location. Let's go to the bearing. It's 2.6. Maybe we can let me see, we can reduce a little bit more. Maybe instead of 5 we can try 4.5. So a little bit narrower, 4.5 and 4.5 the other side. That creates 2.9. Yeah, this is definitely more optimized, very close to the limit. Note that ASDIP Foundation creates the interaction diagram for the two pedestals. So in this case, the loads are quite low, so we can reduce substantially the number of rebars, maybe 3 and 1. So would look like this, a typical pedestal, and the other one as well. 3 top and bottom, and just 1 left and right. Let's use number 6s and number 6s in both cases. And this is typically the interaction diagram of the pedestals. If you go to the Contents tab, you can see the results in a more detailed way. You can see all the results and the controlling combinations, one-way shear, punching shear, sliding calculations. Finally, in the Detail tab, you can see the results in a completely step-by-step way, exposed formulas, and also references to the ACI code for granular checking. Of course, you can see the report, the condensed report. It's 4 pages. You can see it's very well crafted, formatted. Same thing with the detailed report. All the calculations are there. So you can share this information with your coworkers, with your client, with the architect, or with your checker. So it's a very nice tool for your design. Okay, with this we complete the design of this combined footing. Thank you for your attention. We'll see you in the next video.